This is Kirchoff's rules for more complicated circuits. If your circuit is a little more complicated than just a parallel or a series or a combination, and I'll give you an example that aren't too complicated, but that are still you can't solve the other way. Or sometimes even you can, but it's better to do it this way. There are rules for solving those circuits. And these are the two rules. They're called Kirchoff's rules. Kirchoff, by the way, was a contemporary of Bunsen, from Bunsen burner fame. And the two of them did some work on spectroscopy, trying to understand the colors of light that were emitted by burning chemicals. And they noticed that atoms had discrete spectra, and that was, they didn't know they were atoms at the time, but if they got pure compounds and burned them, they would notice that if you looked at them through a prism, there would be specific colored lines, very specific to whatever chemical they were burning, and that was what led to the discovery of atoms. So he did some interesting things besides this. Anyway, so if you're looking at a complicated circuit, Kirchoff says there are two rules you can follow to solve it. The first one is called the junction rule, and the junction rule says that if you have like a resistor here, and the circuit breaks up, and there's a resistor here, and I don't know, a battery here or something like that, right? Then if this is I1, and this is I2, and this is I3, then the current entering the junction adds up to the currents leaving it. In other words, here I1 would have to equal to I2 plus I3, and if you could have 5 of them in there, 5 wires meeting at one spot, and the total current in has to equal the total current out. It's not much different than if it had been water. The water in equals water out. There are no leaks in the system, presumably. And so that's the first rule. It's the junction rule. It's sort of common sense. And the second one is called the loop rule. And what this says is if you go around any loop in the circuit, and I'll give you some examples of this, the total change in electric potential around the loop is 0. So if, in the circuits we've been doing, they just have resistors and batteries. If you look at the voltage increase across the battery and then decrease across the voltage, and you get back to where you started from, you get to 0. And so there are a few ways for sub-rules for this, but we'll talk about that here in a second. So we're going to talk about Kirchoff's rules in the context of this circuit. And so usually when you get a circuit, you have resistors that you identify, and then you have a battery or a power source that you identify. And the first thing you do is identify currents through resistors. And usually you number the currents just the same way that the resistors are numbered. And so if you were to do that here, you would say, well, we could apply the junction rule here. We'll call that A. Right? Well, the current entering A is I1, and the current leaving A, well, this is I2, and this is I3, and so you say I1 equals I2 plus I3. We could do the same thing down here at B, right? And we would say, well, the current entering B is I2 and I3, and since this is all one loop, this is all one section, this part is in series, that's the same current as I1. And so the junction rule gives us the same equation at these 2 points. By the way, it doesn't matter, believe it or not, how you pick the currents. You could have chosen I3 going up and I2 going down. It would change this equation. Instead, if we picked I3 going the other way, it would be I2 equals I1 plus I3. But if you pick a direction wrong, then when you solve, at the end that current will come out negative to tell you that it was actually going the other way. And so normally it's pretty easy to tell which way the current's going, but not necessarily in a really complicated circuit. And if you use Kirchoff's rules correctly, it doesn't matter how you pick it. If you pick it in the wrong direction, it'll come out negative to tell you it went the other way. All right, so now let's look at the loop rule. And that's a little more complicated. First of all, I'm going to identify some loops here, right? And so this is a loop, and we'll call it loop 1. Maybe I'll write it this way. I'll write it that way. Loop 1. It's just any place where you can go all the way around and come back on itself, right? And so I'll make a second one. Here's loop 2. That's loop 2, right? If I go around from A all the way around to B and then back to A, that's loop 2, right? And finally, there's a third loop, which you might not have thought of, but maybe you did. That's just all the way around the whole circuit. And that's loop 3. Right? And so if we want to apply Kirchoff's loop rule to say 1, to loop 1, we just pick a point. And so we call it AB. I'll call this point C and this point D. And we'll just go around the loop from D to B to A, from C to D to A to B to C, right? And so here's the breakdown of the loop rule. So when you're we're looking at the changes in potential around a loop, right, that have to add up to 0. And so the changes in electric potential going from C to D, I'm going across a battery from the short line to the long line, which means from negative to positive, just like here. And so I would add a V. I would add V. If I were going the other way, if I were going around this loop this way, which I could, maybe we'll do that later, I would add a negative V. And so your electric potential increases when you're going up a battery, when you're going from negative to positive, and it decreases, minus V, when you're going from positive to negative. The next rule is when traversing a resistor in the direction of the current, add negative IR. And so if we were going to go from D to A, we would add minus I1 R1. Otherwise, if you're going the other way, if you're going from this direction to that direction, otherwise add IR. Right? And so this is the sort of the breakdown of the two rules when you're traversing a resistor, a battery, and then when you're traversing a resistor. And so let me erase that, and let's go back to this circuit. Right. And so for loop 1, we'll go D, C, A, B, C, D, A, B, C. We're going to go around here and then all the way back to here. And so if we go from C to D, that means we're adding V, right? And then if we go D to A, we're going to say minus I1 R1, because I'm going in the direction of the current, and the voltage drop across the sky is Ohm's law, right? Now I'm going from A to B, and so this is C to D. This is A to B. Nope. D to A. Right? And then minus I2 R2. Right? So I get to here. I'm at A. I'm going from A to B. And then B to C is nothing. And so if I do this around a closed loop, it's equal to 0. And so this is the sum of the changes in electric potential, V minus I1 R1, minus I2 R2 equals 0. That's for loop 1. So if I do loop 2, right, I can start at, what am I going to call this, E, F. Sorry, the letters are a little messed up. And so we can pick anyway. Let's go A, B, F, E, A. So we're going to go around the loop this way. I'm going to say, look, if I'm going from A to B, it's minus I2 R2 because I went in the direction of the current. B to F has no change. F to E, now my resistor is here, but my current's going the other way, so it's plus I3 R3, and that gets me back to my starting point equals 0. And so here's an equation that applies to my circuit. Here's an equation, so I'll call this 1. Well, anyway, this is the first equation that applies to this circuit. I2 plus I3 equals I1. This is the second equation that applies to this circuit. This is the third equation. Remember, if I know all my resistors, I just have 3 unknowns, I1, I2, and I3. And so I now have 3 equations and 3 unknowns. I could solve this circuit. But I could also just write down another equation for the big loop if I wanted to. I could do C, D, A, E, F, B, C. I can go around the big loop like this, and I could say, so C to D is plus V minus I1 R1 minus I3 R3 equals 0. Right? I went around the outside. Notice, just as an example, suppose we did that in reverse. So suppose we did C, B, F, E, A, D, C. Right? So I go from C to B to F, nothing happens. And I go from F to E, and that's plus I3 R3, because I'm going against the direction of the current. Current's going this way, but I'm going that way. Similar here, plus I1 R1. And then I'm going backwards on a battery to get back to C, and so minus V equals 0. And so this equation is from going clockwise, and this equation is from counterclockwise. And notice they give me the exact same answer. Right? If I put the I1 R1 and I3 R3 on the right hand side, I get V equals the sum of these two. If I move my V over, I get V equals the same sum. And so it doesn't matter which way you go around the circuit, and it doesn't matter which way you choose your current, you'll come out with the right answer. And so I'll do a numbers example of this next. So here's sort of a complicated loop, even though it's just one loop, to look at the loop rule. And so it's V1 is a 12-volt battery, R1 is a 10-ohm resistor, R2 is a 20-ohm resistor, V2 is a 6-volt battery pointing the other way. Its positive end is going the other way up the circuit versus V1. And finally, R3 is a 30-ohm resistor. And so if I label the corners A, B, C, D, then if I do a loop for A, B, C, D, and back to A, I have to get a change in electric potential that's 0, and so I get a plus V1 going from here to here. And then since I chose the current this way, right, clockwise going around the circuit, I could have picked it the other way. Then I get a minus IR1. It's all in series, so everybody gets the same current, minus IR2. Now I'm using the loop rule to go across a battery, which has got its positive end upstream, so I'm going against the grain of the battery, and so that gives me a minus V2. And then I'm still going this way, minus IR3, and I'm back to here, right? And so that's my equation. And so if I leave the V's on the left-hand side and move the IRs to the right-hand side, I get this, where I've factored out the current. And then I can solve for the current by dividing the known V's by the known resistors. And it's 12 volts minus 6 volts, that's 6 volts. And then it's 10 ohms plus 20 ohms plus 30 ohms is 60 ohms. 6 volts divided by 60 ohms is 0.1 amps.